Hello, can you hear me? Uh, the stream is unlisted right now. I'm going to make it public soon, but the thing is, I was just streaming right now, and it was very laggy, so that's why I started this stream. Okay, the stream is now live. Can everyone hear me? So I'm going to be reading the discrete math book again. I'm going to read from where I last left off. Okay, so wait, hold on. Last stream, I was reading about logic and proofs. I read this chapter and these two chapters, but the thing is, my stream cut off early. This chapter got recorded, but these two chapters didn't get recorded. So I'm going to reread these two chapters and maybe read the proof chapter as well. Okay, so what I was talking about last stream is this issue with the implication statement. With this truth table, P implies Q. So this is if P, then Q. How this statement works is that if event P happens, then you expect event Q to also happen. So if P is true and Q is true, then this statement holds. If Q is not true, like let's say in this example, I press a button, that's event P. And then event Q happens where this light switches on. So if I press the button and the light switches on, if P happens and Q happens, then if P, then Q, this statement holds. If Q is not true, so if the light is not on and the button is not pressed, then the statement also holds. If P, then Q. Because if you're saying that if I press this button, then the light is on. If the light is not on, then you would expect the button to be not pressed. Also, if the button is pressed and the light doesn't get on, then this statement doesn't hold. That is intuitive. But the issue is for P implies Q, this is true. Like in this case, when P is 0 and Q is true, this statement still holds. So if P doesn't happen, Q happens, then the statement still holds. So there could be other reason Q happens. Maybe some other button got pressed, like let's say event M, some other button is pressed, and then Q happens. So Q can happen without P happening. But the problem with this last statement is if I say if P is something definitely false, like let's say if 5 is even, then 6 is greater than 3. P is false, Q is true, but the entire statement is considered true. So what I said last time that there should be P implies Q should be a general statement which only contains three rows, not the last one. And then there should be a separate logical connector called P implies Q where the default is true. P Q. P implies Q where the default is true. This is like it's assumed to be true unless proven otherwise. So assumed to be true unless proven otherwise. And then we have the other one which has P if and only if Q. So this will work if, yeah. Wait, I made a mistake. True. False. So if P happens, Q doesn't happen, then if P, then Q is false. Okay. So so there should be this statement. This statement already exists in our books. This is what I was proposing that we should have like a default true statement and we should have like a general statement how we use it colloquially. And there should be like 0, 1, question mark. This is general, these two are specific. So P if and only if Q means like only event P makes Q happen. There's no event M. So this doesn't exist. There's no event M. So if P happens, then Q happens. If Q does not happen, then P does not happen. And this cannot be true that P happens, Q did not happen. And this cannot be true that P does not happen, but Q happens. Right. So let's go on reading. And let me check how my stream is doing before actually start reading. Because the last I checked, it was like very laggy. Yeah, I feel satisfied for now. So implications. Little Timmy's mom tells him, if you don't eat all your broccolis, then you will not get any ice cream. Right. So event B is whether he gets his broccolis. Event I is whether he gets the ice cream. So no broccoli, then no ice cream. I should get rid of this. Little Timmy mom says that no broccoli, no ice cream. I should do this. This is a negation. So his mom said no broccoli, no ice cream. This statement should hold. Let's assume that this statement holds. If the mom is truthful, then this should hold. No broccoli. He gets the ice cream. And this would be false, right? Yeah. If he gets the broccoli and he gets the ice cream, And this is also true. But the thing is, we did not talk about we did not talk about this case where he eats the broccoli. His mom said, if you don't eat all your broccoli, then you will not get any ice cream. Of course, Timmy loves ice cream, so he eats all of his broccolis. But his mom does not talk about the case where if he does eat all the broccolis. She only talks about the case where he doesn't eat the broccolis. After dinner, when Timmy asks for his ice cream, he is told no. Does Timmy have a right to be upset? Well, no, he doesn't because his mom's statement still holds. An implication is a molecular statement of the form P implies Q, where P and Q are statements. We say that P is a hypothesis or an antecedent. Q is the conclusion or a consequent. Look in particular at the third row. So false, true, true. This is the confusing bit. Consider the implication. If 5 is less than 3, then 5 plus 3 is equal to 8. Does that statement feel true? The truth table says it should be. Yeah, but the third row is the annoying. Well, the third row here is the fourth row here. Yeah, I did this last stream, so these are already checked. So an implication is the way of expressing a relationship between two statements. It is often interesting to ask whether the other relationships between the statements, whether there are other relationships between the statements. Here, we introduce some common language to address this question. Given an implication, P implies Q, we say the converse is the statement Q implies P. So the converse is Q implies. Okay. So we have P implies Q. The converse, this looks ugly. Converse, we have the converse, we have the contrapositive, we have the inverse. Contrapositive, and we have, what is this doing here? Inverse. So converse is when these are flipped, when we are saying Q implies P. If both of them are true, then we have this if and only if this. So if P implies Q is true, like normally in our textbook, P implies Q is this right here. If P implies Q is true, then not Q implies not P is true. This is the contrapositive. And the inverse, I think it's not P implies not Q. In considering statements with quantifiers, we ignore the outside quantifiers when forming the converse, contrapositive, and inverse. Okay, so it's the same when we say for all. Uh, True or false, if you draw any 9 playing cards from a regular deck, then you will have at least 3 cards, all of the same suit. If you draw any 9 cards from a regular deck, then you will have at least, okay, I'm not good with cards, at least 3 cards, all of the same suit. Is the converse true? So the converse should be, if you have 3 cards, wait, what's the converse? Contrapositive, if you don't have at least 3 cards, all of the same suit, then you don't have 9 cards. It is easy to see why this is true. If you don't have at least 3 cards in a suit, you can have at most 2 cards of each of the 4 suit for a total of Most 8 cards. Converse, if you have at least 3 cards of the same suit, then you have 9 cards. This is false. You can have 3 spades and nothing else. Okay, I don't understand this example. Suppose I tell Sue that if she gets a 93% on her final, then she will get an A in the class. Assuming that what I said is true, what can you conclude from in the following cases? So she gets 93 on her final, then that means she gets A in her class. Sue gets A in the class. We can't conclude anything because this may not be the only condition. Like there could be, I don't mean condition, like any, this may not be the only cause. There could be other causes like extracurricular stuff that will lead her to get an A. See, we can't make the conclusion that she got a 93. She does not get a 93% on her final. So this is about Sue getting a 93%. If she does not get a 93%, then we don't know if she gets an A or doesn't get an A. This is inconclusive as well. If Sue does not get an A in the class, then that means the thing that leads to getting an A also did not happen. So she did not get 93%. We include the necessary and sufficient versions because there are common, those are common when discussing mathematics. Let's agree once and for all what they mean. P is necessary for Q means if Q happens, then P would happen. Okay, P is necessary for Q. That means if Q is true, then P should also be true. P is sufficient for Q. And that means all you need is P and then Q would also be true. P is necessary and sufficient for Q, then P if and only if Q. Rules of logic. Yeah, I did this last time, but I was unsure about this. It took more time than I expected. They don't give answers. That's the issue. Otherwise, I would have done it again. Consider the statement whenever Holmes wears a purple shirt and the green vest, he chooses to not wear a bow tie. Let P be the statement Holmes wear a purple shirt. All right. G be the statement Holmes wear a green vest. All right. B be the statement Holmes wear a bow tie. Well, he did not wear a bow tie, which is the best translation. It is D. So P and G. If this, then this, then not B. Consider this statement: Holmes wear a green vest unless he is also wearing either a purple shirt or red shoes. So if Holmes never wears a green vest unless he is also wearing either a purple shirt or red shoes. So that means that if he is wearing a green vest, that means he is wearing a purple shirt or red shoes. So then it's this one. Wait, let's answer a question about Monopoly. Analyze the statement. If we get more doubles than any other player, okay, let's just skip this. Statement about monopoly is an example of tautology, a statement that is necessarily true based on its logical form alone. Tautologies are always true, but they don't tell us much about the world. No knowledge about monopoly was required to determine that the statement was true, and thus knowing that the statement is true tells us nothing about monopoly. Logical equivalence, you might have noticed in example 1.3.2 that the final column in the truth table, not P or Q, is identical to the final column in the truth table, P implies Q. So true, false, true, true in both cases. Th- This is that no matter what P and Q are, statements not P or Q and P implies Q are either both true or both false. We therefore say these statements are logically equivalent. And we write this as P, three lines, and then Q. And implication is logically equivalent to its contrapositive. So P implies Q is equivalent to not Q implies not P. So we have De Morgan's laws. The negation of a disjunction or conjunction is logically equivalent to the conjunction or disjunction of negations. So not P and Q is equivalent to not P or not Q. Not P or Q is equivalent to not P and not Q. This suggests there might be some sort of algebra you could apply to these statements. Okay, there is. It is called Boolean algebra. Okay. De Morgan's laws do not directly help us with implications, but as we saw above, every implication can be written as a disjunction. So every implication can be written as a disjunction. You have double negation, negation of an implication. So we are just negating both sides, right? Equivalence for quantified statements. Sometimes quantifiers have nothing to do with equivalence. For example, yeah, we can add for all on each side. To dispute a universal claim, you just need one single counterexample. You just need to show there exists a number for which the claim is false, in our case. So if we want to dispute for all x, so all odd numbers are prime. If you want to dispute that for all x, if x is odd, then x is prime. We need one single counterexample. We need to show that there exists an x which is odd and not prime. If we ignore the quantifiers for a minute, we are left with not O implies P equivalent to O and not P. This is exactly the same as theorem 1.3.9. 1.3.9. Negation of an implication. So not all x, px is equivalent to there exists x, not px. Because so the negation is inside, and then negation of there exists x is equivalent to all x, not px. Yeah, that makes sense. If there is an x that is not prime, if there doesn't exist an x that is, let's say, that fulfills p, we need to show for all x that none of them fulfill p. Consider the two statements. Are these logically equivalent? I would say no. Intuitively, the statement on the left claims everything is either P thing or Q thing. The statement on the right claims that everything is either a P thing or that everything is either a Q thing. These feel different. Deductions. Earlier, we claimed that the following was a valid argument. If Edith, if Edith eats her vegetables, then she can have a cookie. Edith ate her vegetables, therefore Edith gets a cookie. How do we know this is valid? Let's look at a form of the statement. Let P denote Edith eats her vegetables. Let Q denote Edith can have a cookie. The logical form of the argument is uh, P implies Q. We have P and then Q. This is an example of a deduction rule, an argument that is always valid. This one in particular is particularly famous, called modus ponens. So P implies Q is true. We assume that this part is true. So we have this case, we have this case, and we have this case. And also P is true. So we have this case only, right? So this is true means Q is true. Show that the following so to show that the following is a valid deduction rule. P implies Q, not P also implies Q. So every time either P would happen or P would not happen, either way Q always happens. But they need to see it via truth table, right? P implies Q, true. Not P implies Q, true. And Q is true. Over here as well, Q is true. Implies R, Q, if P then R, if Q then R happened, that means P or Q happened. Again, we would have to use a truth table. This is, I guess, obvious. All X are P thing, then there exists an X that is a P thing. Wait, hold on. Wasn't there a question about trolls? Did we do that last stream? Not this one. There were three trolls. Hold on, let me see if it's an implications. It's not here. Was it here? Maybe I did it last stream. I did it last stream, but I don't know if it's in the cutoff section. Yeah, I did it here. What about the chest one? Never mind that. Rules of logic. Okay, let's see what that question was. Which of the following statements is a law of logic? That is, which of the following are true no matter what your domain of discourse is and no matter what you interpret the predicates as meaning? Select all that apply. So for all x, either x is p or not p. So okay, this is always true. So for all x, it is not true that all x is p. This implies that there exists an x which is p. Yeah, this will always be true. This is not true. I think this is also true. For all x, there exists y for which pxy is true. There exists a y for which all x. There exists a y such that for all x, pxy is. No, this is not. Got two answers and got one correct of one needed. Why is this not correct? Uh, for all, it is not true that for all x. Oh, because it could be possible that for none of the x, px is true. Yeah. That makes sense. I come upon three trolls fully wearing name tags. They say, Pat, if either Coin or I are knights, then so is Ryan. Ryan is a knight, and if Pat is a knight, then so am I. Coin is a knave, but Pat and I share the same persuasion. Create a truth table that includes all three statements, then use the truth table to determine the persuasion of each troll. So whether they're a knave or a knight. Uh, yeah, there's so we have Pat, Coin, and Ryan. We have 0, 0, 0, 0, 0, 1. I just copy and paste. 1, 1. Let's just copy this. And 1, 1, 1. How do I? Okay, never mind. Actually, let's bring this. So let's say all three are liars. Let's say all three are knaves. If either Coin or I are knights, then so is Ryan. But if all three are knaves, so Ryan is a knight. If Pat is a knight, then so am I. Ryan is a knight would be false, right? Coin is a knave. Coin as a knave would be false, right? Coin is a knight. So this can't happen. Wait. If Ryan is a knave, then queen is a knight. But if queen is a knight, then Ryan is a knight. So Ryan cannot be, that will lead to a contradiction. So these ones can't happen. Uh, if Ryan is a knight, Ryan is a knight, queen is a knave. Queen is a knave, then Ryan is a knight. If queen is a knave, if this is true, then Ryan is a knave. Hold on, that doesn't make any sense. Ryan cannot be a knight or a knave because both lead to a contradiction. Ryan, if Ryan lies, if Ryan is a knave, then queen is a knight. And queen says Ryan is a knight. If Ryan is a knight, if Ryan is a knight, the queen is a knave. Okay, it could be that queen is a knave. This statement is true, but this statement is false. So the entire statement is false. So queen. So the only one that makes sense is if Ryan is a knight and queen is a knave. So if Ryan is a knight, then queen has to be knave. So one of these two. If Pat is a knight, and so am I. Ryan is a knight. Pat and I share the same persuasion. So Pat is a knight. If either queen or I are knights, then so is Ryan. Pat is a knight. If Pat is a knight, then so am I. But this statement is false. So queen is a liar. 8. So we have knight, knight, knave. This is the correct statement here. So knight, coin is a knave, but Pat and I say share the same persuasion. Knight, if either coin or I are knights, then so is Ryan. Pat is a knight, so these two statements hold up. Coin is a knave, Ryan is a knight. This statement is true, but the entire statement is false. And if Pat is a knight, then so am I. So this statement is false. Yeah, so that makes sense. A mini Sudoku puzzle is a 4x4 spread of squares divided into 2x2 boxes. Goal of each square with a digit from 1 to 4 such that no digit repeats in any row or any column or any box. Here is a mini Sudoku puzzle. You can try solve. Copy. How do I get rid? Yeah. Uh, Paste. Copy. And I don't know why it's not working. So 2143. 2, 4. Yeah, I have an idea. So when they say box, they mean this box over here. I should take in this line. Uh, like that, that, like that. So we have no small 2, 4, 1, 3. And we need to solve this, right? You can't have 1 here. Wait, I will fill in my. Should I pink? We can't have 1 here, so 1 has to be here. The 3 has to be here. So 4 has to be here. 3 cannot be here. 3 has to be here. 2 here. And 1 here. So 1 here. And 2 here. 2 has to be here. 4, 4, 3, 3, 3, 4, 4. Now I notice that the solution of the above puzzle has 4 outside corners all different and its 4 middle squares all different. The goal is to investigate. Question is to prove that this is not a coincidence. Suppose a mini puzzle has all different numbers in its 4 corners marked with this. Prove that the center of 4 squares marked with asterisk must also contain different numbers. If you have different numbers here, then there should be different numbers here, right? Contradiction. Otherwise, you might have the same row in the like. It's going to take time. Different numbers here. You can't have same. You can't have same number here, because that will lead to a contradiction. So you need different numbers here in these two and different numbers in these two. So at least, for example, 1, 1 and 2, 2. So you can have, okay, but if you have different number on each, I think the same argument would apply here as well, right? These four, like either these two are different or these two are different. You cannot have one in the same row or in the same column. You can, but you can have one and one. Now, if all of these numbers are different, then can have like 1, 2, 2. So for example, 1, 2, 3, 4. 1, 2, 3, 4. You can have 1, 1, 2, 2. But there's a problem here. If these two numbers matches this number, then this last slot belongs to the that number. So if it's like 1, 1 and 1 over here, then 1 can only go here, nowhere else. But if these two numbers are different, then these two numbers would have to be different as well. Something like that. Anyone who doesn't believe in creativity, anyone who doesn't believe there is creativity in mathematics clearly has not tried to write proofs. Finding a way to convince the world that a particular statement is necessarily true is a mighty understanding and can often be quite challenging. There is no guaranteed path to success in the search for proof. For example, in the summer of 1742, a German mathematician by the name of Christian Goldbach wondered whether every integer greater than 2 could be written as a sum of two primes. Centuries later, we still don't have a proof for this apparent fact. Writing proofs is a bit of an art. Like any art, to be truly great at it, you need some sort of inspiration, as well as some foundational technique. Consider the statement: if A, B is an even number, then A or B is even. Which of the proofs below appear to be valid proofs of this statement? Note, you can assume all the algebra below is correct. Suppose A and B are odd. That is, A is 2k plus 1, B is 2m plus 1. For some integer k and m, then, or then we can use the contrapositive here. And if A is odd and B is odd, then AB is odd. Assume that A or B is even. Say it is A. I think this should be enough, right? Because the negation of this is that either A or B is even. Yeah, the contrapositive is if A or B is even, then AB is even. Assume that A or B is even. Say that it is A. That is A is equal to 2k for some integer. Then AB is equal to 2kb. And then AB is even. But the thing is, this proves that if A or B is even, then AB is even. Suppose that A, B is even, but A and B are both odd. Namely, A, B is 2 and A is 2k plus 1 and B is 2j plus 1 for some integers n kj. Then you have this. Since 2kj plus k plus j is an integer, this says that the integer n is equal to the non-integer, which is impossible. Which of the proofs above are valid proofs of the statement? Proof 1. Proof 1 is, oh, we need to collect multiple. Proof 2 is not valid. Proof 4, let AB be an even number. Say AB is to n. Proof 3 is valid. Proof 2 is not valid. Uh, okay. The simplest style of proof is called direct proof. Often, all that is required to prove something is a systematic explanation of what everything means. You look at the definitions, carefully explain and unpack their meaning until you see that their conclusion is true. To illustrate the importance of definitions in a proof, let's give a few careful definitions about mini Sudoku puzzle. A mini Sudoku puzzle is partially filled in 4 by 4 grids of squares. Okay, we already know this. We say that a mini Sudoku puzzle is solvable if there is exactly one solution. First, let's prove a useful and obvious fact about any valid mini Sudoku puzzle. Any solution to a mini Sudoku puzzle will have each digit from 1 to 4 appear exactly once in each row, in each column, in each box appearing a total of 4 times. That's obvious. You say, isn't that exactly what a valid puzzle is? Well, a valid completed puzzle, which is what we mean by solution, right? They're not exactly, since a valid means no digit repeats. Isn't that the same thing? Yes, exactly. Saying this is a direct proof. Suppose you have a solution to a mini Sudoku puzzle. That means you have a 4 by 4 grid with each square filled in with digits 1 from 1 to 4 that is valid. Since the puzzle is valid, no digits repeat in any row, any column, or any box. Since a row contains 4 numbers that do not repeat and there are exactly 4 possible digits, each of those digits must appear exactly once. This is true for every row and for every column and for every box. Uh, let's prove something about a particular Sudoku puzzle. Prove that for any solution to the mini Sudoku puzzle below, if the solution has a 2 in the top left square, R1C1, or they're talking about this, then it will contain a 2 in the bottom right square, R4C4. Yeah, because if 2 is here, then 4 has to be here. But if 4 is here, 1 is here, 3 is here, then 2 has to be here. Observe the general form of the argument above. We are trying to prove an implication. P implies Q. If there was a 2 in R1C1, then there was a 2 in R4C4. We started by assuming P was true. From that, we deduced something, and from that something, we deduced Q. This is exactly what a direct proof of an implication looks like. Assume P, explain, therefore Q. One additional consideration we must take is that often we are proving a general universal statement, a statement of the form for all x, P of x implies Q of x. To handle the quantify, we fix an arbitrary instance of x. Above, we said let S be a solution to a puzzle. Since we made no additional assumption about S besides that P was true about it, we say that S was an arbitrary solution. If we wanted to prove that all squares are rectangles, we first realize that this is the same as saying for any shape, if the shape is a square, then it is a rectangle. In symbols for all x, if x is S, then x is R. If, wait, we will want to assume P x is true and deduce Q. What x do we use? An arbitrary one, so our proof can be applied to all possible x. Proof that for any mini Sudoku puzzle with 3 empty squares, if the puzzle has a solution, then the puzzle is solvable. There are 3 empty squares, right? If there are three empty squares, then there has to be one row, like a row or a column where only one square is missing. And we can solve that one square. Let P be an arbitrary mini Sudoku puzzle. Assume P has exactly three empty squares and that S is the solution. Since P is arbitrary, you don't know how the three empty squares are arranged. They could be all in different rows, or two could be in the same row, or all three could be in the same row. If all the empty squares are in different rows, then in each row there is exactly one empty square. The other three squares are filled with three different digits. Oh, that's just what I said. So there is only one choice to fill the empty square. This number must be the number used in the solution S. Now consider the case where there are two empty squares. The two empty squares are in the same row. Third square is in a different row. Or we can use this. There are columns with one missing, right? Like I get the solution, but explaining it would be take quite some time. Direct proofs, of course, can of course be used to prove statements in mathematics too. For all integers, n if n is even, then n squared is even. Yeah, we write n as 2k, and then we are left with 4k square, which is even. For all integers a, b, and c, if b is a multiple of a and c is a multiple of b, then b is a multiple of c. So if a is equal to kb, no wait, b is a, if b is equal to ka and c is equal to jb, then c is all equal to jka, right? So c is a multiple of a. Prove by contrapositive. Recall that an implication is logically equivalent to its contrapositive. Not Q implies not P. There are plenty of examples of statements that are hard to prove directly, but whose contrapositive can easily be proved using a direct proof. This is all that proof by contrapositive does. It gives a direct proof of the contrapositive of the implication. This is enough because the contrapositive is logically equivalent to the original implication. Assume not Q, explain, 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 therefore not P. Prove that if a mini Sudoku puzzle is solvable, then it is valid. Well, if it is not valid, then it is not solvable. Remember, a puzzle is valid provided no rows, columns, or box contains a repeated digit. A puzzle is solvable if there is exactly one solution. The solution is a valid puzzle with no empty squares. I mean, by definition of solvable, if it is solvable, then it is valid, right? We can use direct proof here also. Let P be an arbitrary many Sudoku puzzle. Assume that it is not valid. This means there is at least one row or one column or one box that some digit appears more than once. Now suppose we have filled in the empty squares but not changed any of the previous filled in squares. The original row, column, or box that contain a duplicate digit will still contain that duplication. So the resulting completed puzzle will not be valid. Thus no solution to P exists. So P is not solvable. Take a step back and consider what it would mean if the conclusion of an argument were false. There are two reasons this could happen. Either the logic of the argument is faulty, or at least one of the assumptions must be false. A proof by contradiction exploits the second possibility. You start with a single assumption and construct a valid proof that leads to a false conclusion. The only possibility is that the single assumption was false. False conclusion is the contradiction, which just means a necessary false statement. Note that if we think of this style of argument as a direct proof of something, it is a direct proof of not P equals contradiction. Once you start writing proofs by contradiction, it becomes very natural. Let's see. Okay. Prove that root 2. Wait, let me try to remember the proof that root 2 is irrational. Root 2 can be written as m over n, where they both are integers. Square both sides. No, wait. Wait, I can't remember the proof of this. Is it like this? Hold on, let me. Suppose not that 2 root 2 is equal to a fraction a over b without loss of generality. Assume a b is in its lowest terms. Wait, I was correct. So 2b squared is equal to a squared. Thus, a squared is even, and as such, a is even. So a is equal to 2k for some integer. We then have b squared is equal to 4k squared. So b squared is equal to 2k squared. Thus, b is even, and as such, thus b squared is even, as such b is even. Since a is also even, we see a over b is not in its lowest term, a contradiction. Thus, root 2 is irrational. There are no integers x and y, such that x squared is equal to 4y plus 2. Oh, because if we take the 2 out, we are left with 2 times 2y plus 1. So 2 times an odd number. 2 times an odd number gives an odd number, but x squared is even. So we have direct proof, contrapositive, and we have contradiction. Okay, let's go to the next chapter. It was this. Arrange some of the statements below to form the correct proof of the following statement. For any integer n, if 7n is even, then n is even. Hold on, wait, what? Wait, let me see the solution for that. Since this implies that x is even, x is equal to 2k for some integer k. X squared is equal to 4k squared. This in turn gives 2k squared is equal to 2y plus 1. But 2k squared is even, 2y plus 1 is odd. So these cannot be equal. Thus we have a contradiction. So 7n is even means it's divisible by 2. 7 is not divisible by 2, so n has to be divisible by 2, right? This would be the last statement. Let n be an arbitrary integer and assume that n is odd. 7n must be odd. Let n be an arbitrary integer and assume n is odd. 7n must be odd. No, this is not necessary. Odd time odd is even. Wait, hold on. Uh, we need this. Assume 7n is even. 7n must be even. No, we assume that it's even. Since 7 is odd and the product of an odd number with an even number is even, then n must be even. Highlighted blocks in your answers are wrong or in the wrong order. Let n be an arbitrary integer and assume 7n is even. Since the 7 is odd and the product of an odd number with an even number is odd. So 7 is odd and the product of an odd number and an odd number is odd. Since an even number divided by 7 must be even. Are we proving by contradiction? Since the 7 um okay, let's try this. Let n be an arbitrary integer and assume n is odd. Assume n is odd. Since 7 is odd and the product of an odd number, 7 is odd and the product of an odd number, and an odd number is odd, 7n must be odd. Perfect. Okay. So we are proving by contradiction. We're proving the contrapositive, right? Okay, we'll just go to the next chapter then. Suppose there are 15 people at the party. Most people know each other already, but there are still some people who decide to shake hands. Is it possible for everyone at the party to shake hands with exactly 3 other people? 15 people at a party. Most people know each other, but there are still some people who decide to shake hands. Is it possible for everyone at the party to shake hands with exactly 3 other people? Wait. So one person shakes hands with another person who shakes hands with this, this, this. Then this person shakes hands with this guy, and this guy, and this person shakes hands with this guy, this guy, this guy. This person shakes hands with this guy, this guy, this guy. So four people shake hands with each other. So you have four people where each person is shaking hand with exactly three other people. Is it possible for everyone at the party to shake hands with exactly three other people? So four, 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 four. We have 16. Hold on. Four, four, four. We have 12. 16 people in total, but let's remove this one. And if he shakes hands with him, he shakes hands with this guy, then right? I don't think it's possible. I need the answer of that question. So far, we have seen how the logical form of a statement can inform how to build the scaffolding of a proof. This can only get us so far, though. To flesh out the proof skeleton requires an understanding of the mathematical objects and the structures the proofs are about. Some of this can come from carefully reading definitions, yet there is some less concrete understanding and intuition that comes from working with objects and structures that can lead to that aha moment of inspiration. By rewriting proofs, besides practice in becoming better reasoners, diving into careful proofs about discrete structures is the best way to learn about structures themselves. Okay, let's just go to the activity. Explore some basic properties of sets and functions. Later in this section, we'll write proofs about these ideas. Remember that a set is just a collection of elements. Here are two definitions about sets. A set A is a subset of a set B, written A subset B, provided every element in A is also an element of B. Given sets A and B, the union of A and B, written A union B, is a set containing every element that is in A or B or both. Okay, let B be this. Give an example of a set A containing three elements that is a subset of B. Let's just say 1, 3, 5, just the first one. Union. Give an example of two distinct sets A, B, such that A union B is equal to B. So A would have to be an empty set, right? Or the example you give is A subset of B. The answer is yes. A null set is a subset of every set, right? Which of the following are always true? For any set, if A is a subset of B, then A union B is a subset of B. No. Wait, yeah, that's true actually. A is a subset of B, then A union B is equal to B, right? Wait, that answers our previous question as well. A is a subset of B, then A union B is equal to B. Any such A and B, if A union B is equal to B, A is a subset, yeah. Any set A and B, if B is a any set B is a subset of A, okay. Or any set A and B, A union B is a subset of B. No, that's not true. Because A union B is not a subset of B. Recall that a set is an unordered collection of elements. We can describe a set by listing these elements or by specifying a property that all elements in the set satisfy. For example, 1, 2, 3, 4, 5, or X is all natural numbers where X is less than 10. Okay. The second set is a set of natural numbers. No, this N over here is a set of natural numbers. Oh, set of natural numbers less than 10. Notice that every element in A is also an element of B. Here is the definition that captures that idea. A subset, a set A is a subset of set B written A subset B provided every element of A is also an element of B. Set B is sometimes called a superset of A. We say A is a proper subset of B written A, what do you call this notation? A proper subset B, provided A is a subset of B and A is not equal to B. It's like less than, it's analogous to less than and less than or equal to. Any sets A, B, and C, if A is a subset of B and B is a subset of C, and then A is a subset of C, this is trivial. A function f from set A to set B is a rule that assigns each element of set A to exactly one element of the set B. It is any rule. There doesn't have to be a formula or rationale for it. You just need to match up elements from A to elements in B. For example, we could let A be a set of students enrolled in particular discrete math course. B be the set of months in year. Now the definition of A to B be a rule that assigns each student the month in which their birthday falls. Since every student has an assigned month and no more than 1 month, this is a function. So we have the domain, we have the range, A, B. So a function would be like assign this to this, assign this to one of the element. It could be the same element as well. So, so what a function cannot do is like assign one element to multiple elements. Assign one element to multiple elements in B. But it can do this, however, assign two different inputs to the same output. Why isn't the eraser working? A function is injective provided every element in B is the image of at most one element in A. In other words, no element is the output for more than one input of A. So basically, a function is allowed to do this. But if, for example, it doesn't do this, every input goes to one unique output, a different output, then the function is called one-to-one. In the example below, we use the two-line notation to describe a function. The top row contains the input and the bottom row contains the list of the corresponding outputs. So 1, 2, 3, 4 to A, B, C, D. Might be defined as, oh, this is a matrix, right? Let A be this, B be this. Consider the function A to B and G from A to B defined like this. So 1 to 2, 2 to 8, 3 to 6, and then G 1 to 4, 2 to 6, then 3 to 4. The input is 1, 2, 3, and the output is this. Which of these functions is injective? This, right? Because this is now 1 to 1. They're like multiple inputs that goes to the same output. Suppose f a to b is a function with a and b both finite sets. If the elements of a is more than the elements of b, then f is not injective. Oh, because there are more inputs than outputs. Suppose a class has 25 students. Then at least 2 students share the same birthday. Oh, because the 25 is more than 12. So you need to have multiple students sharing the same month. You cannot have one to one. Given a function f x to y and a set x is less than or greater, a is less than or greater, sorry, a is a subset of x, we define the image of a under f to be the set f of a, where f of a is an element of y and a is an element of a, of set a. That is, f a is the set of all outputs of the function for inputs in a. Oh, I see. Okay, okay. Let f n to n be defined by f of n is equal to 2n. Let set a be 1, 2, 3. Find f of set a, the image of a under f. That would be 2, 4, 6, right? Yeah, 2, 4, 6. So like the output could be a very large set, but the image is like only the actual outputs itself, only the actual assignments themselves. Let f x to y be a function. Let set a and set b be subsets of x. If a is a subset of b, then image f of set a is a subset of f of set b. A and b are subsets of x. Is a subset of b. Okay, okay, I understand. Because this is like, let's say this is set C over here. And then set B is like, this is set B. Is A subset of B? Yeah. I just switch. B, A. And then, wait. This is Y. This is inside X. So we have more, lots of inputs. We have B, which are some inputs, subset A, which are some inputs, which is a subset of B. So all the assignments of A, so all the f of A part, all the f of A part is included inside the f of B. F of B would be the larger one. Then f of A would be the smaller one. So that makes sense. A relation on a set is a set of ordered pairs of elements. A relation on a set A is a set of ordered pairs of elements from A. You can think of a relation as a way to describe a type of relation between elements of A. For example, we have a relationship on a set of people at a party that describes who is a friend with whom. You might have a relation on a set of natural numbers that describe which pairs of numbers are related by the relation x is less than y. Often relations have special symbols like equal to, less than or equal to, or I don't know what this is. When you talk about the general relation, we use either this and write x. I don't know what this notation is. X something y, or use a capital letter like R and write relation of x and y, or r x r y, or even xy is an element of R. Relation R on a set A is transitive provided xyz if x r y and y r z, then x r z. So relation from x to y, relation from y to z, then relation from x to z. Consider the relation this on a set of students in your discrete math course that holds two students, provided they have some other class together. Okay, so the relation holds of two students. Is this relation transitive? Provided they have some other class together. Wait. So students in discrete math course have A, B, C, D. So if hold on. Provided they have some other class. Okay. So if A and B have some other class together other than discrete math, then A, B is part of the relationship. B, C has some other class. Let's say A, B are doing a biology class and B, C are doing a chemistry class. And A, B have a relation and B, C have a relation. However, it is not true that this B, C are in, these are both separate classes. Oops, what did I do? No, not necessarily. Proving that a relation is not transitive takes nothing more than finding a counterexample. Perhaps slightly more interesting would be a proof that a relation is transitive. Consider a set of all students in your discrete math class. Define a relation that holds students A and B, so A, B is true, provided A is taller than B. Prove that this relation is transitive. Okay, so if A is taller than B, then A, B is in an element. Does the ordering? Yeah, it's a tuple, right? So the ordering matters. So A is taller than B, B is taller than C. And that means this relation holds that A is taller than C. How would you prove such a thing? We can prove by contradiction, maybe. Let A, B, and C be arbitrary students in your discrete math course. Assume A is taller than B and B is taller than C. That means A is taller than B and that B is taller than C. But then surely A must be even taller than C. Then they are taller than B. So we have A taller than C is true as well. Let's spend all of chapter 2 studying proofs about graphs since this is a rich area of mathematics. A graph is a set V of vertices and a set A of edges. The edges are two elements two element subsets of the vertices, and we can think of them as representing relationships between the vertices. Note that this is an abstract definition of a graph using sets, but we often draw graphs using dots for the vertices connected by lines for the edges, as this gives us a nice picture of what is going on. Since graph represents a type of relationship between elements, we can use graphs to represent many real world problems. So graph is a relation, right? A relation between vertices and edges. Maybe? No, no, I don't think. Because a relation is between two elements, right? Set of ordered pairs on a set A is a set of ordered pairs of elements from A. Okay, okay. So I don't think graph is a relation. It's a type of relation, like a different type maybe. Each edge can represent a handshake between two people. Maybe the edges can be a relation. So if you wondered whether it is possible that 15 people at a party each shake hands with three people there, we are really asking whether there is a graph with 15 vertices where each vertex belongs to three edges. One, two, three, one, two, three, one, two, three, one, two. Right, we can have one is here. No, then we have three, right? So three handshakes here, three handshakes here, three handshakes here. So this is three. This guy has done two. This guy has done two. This guy has done one. Unless we do this. Now this guy has done three. This guy has done two. This guy has done two. Uh, yeah. Two. Let me think. We have one, one, two, and three. One, two, and three. So this guy has done three. This guy has done two. So three here, three here, three here, three here. This is three. This is two though. Maybe we can do three here. So this guy has three edges. Can do this. So this guy has three edges. And then three. This guy has done three, but this guy is left with two. Yeah, I don't know. Uh, so if we wondered whether it is possible for the 15 people at a party to each shake hands with three people there, we are really asking whether there is a graph with 15 vertices where each vertex belongs to three edges. Belongs to, yes, because edge is a two element subset of the vertices. So if an edge touches or comes out of a vertex, that means the vertex belongs to that particular two element subset. It may be a vertex on graph G. The degree of the vertex written dV is the number of edges that contain V. The number of edges incident to V. Consider the graph G with the vertices V, 1, 2, 3, 4, and the edges E. So 1, 2, 1, 3, 1, 4, 2, 3. Wait, edges doesn't have to contain ordered pair, right? So it's not really a relation. Unless there's a special type of relation where the pairs aren't ordered. Maybe for a directed graph. What is the degree of each vertex in G? So 1 connects to 2, 1 also connects to 3, 1 connects to 4. So 1 has a degree of 3, 2 has a degree of 2, 4 has a degree of 1, 3 has a degree of 2. So 3, 2, 2, 1. So is it possible for 15 people to each shake hands with exactly three people in their group? Well, there is a graph with 15 vertices. Is there a graph with 15 vertices? All of degree 3? The answer is no. One way you can see this is if you ask how many edges such a graph would have, each vertex is incident to 3 edges. So counting indices, we get 15 times 3 is 45. But every edge is incident to 2 vertices, so we have counted each edge twice. So the number of edges in such a graph would be 45 divided by 2, 22.5, but the number of edges in a graph must be a whole number. So there is no such graph. This suggests that we can say something more in general. The following proposition is a simple consequence of the handshake lemma 2.1.8, which will be proved in section 2.1. In any graph, the number of vertices with odd degree must be even. Okay, I understand. So the degree of vertices is the number of vertices with odd degree must be okay. I will need proof of this. We'll prove this by contradiction. Suppose there was a graph with odd number of vertices with odd degrees. Consider the sum of the degrees of all vertices. Sum of the odd degree vertices would be odd. Okay. So we have degrees is the number of edges, right? Yeah. So the number of edges touching the vertices would be odd. Number of, yeah, the degree of the vertices would be odd. Well, the number of edges would be half of that. The sum, no, wait. No, that's not true. It doesn't have to be half exactly. The sum of the even degree vertices will be even. Sum of odd number and an even number is odd. So the sum of all the degrees will be odd. The sum of odd degree vertices would be odd. Consider the sum of the degrees of all the vertices. The sum of for the odd degree vertices would be odd. So suppose there was a graph with an odd number of vertices with odd degrees. The sum for the even degree vertices will be even. Any sum of even numbers must be even. The sum of an odd number and an even number is odd, thus the sum of all degrees will be odd. However, the number of edges on the graph is half the sum of the degrees, or simply because each edge contributes one to the count of the contributes one to the count of the degree of two vertices. Since the number of edges is a whole number, we see that the number of degrees must be even. This contradicts what we found in the previous paragraph. Wait, hold on. Suppose there's a graph with odd number of vertices with odd degrees. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Here are 14 vertices with 3 edges, right? And there is one vertex with 2 edges. But suppose this was connecting somewhere. We have 15 with 3. So we have odd number of vertices with odd degree. Consider the sum of the degrees of all vertices. The sum for the odd degree vertices would be odd. Sum of the odd degree vertices. Suppose there was a graph with an odd number of vertices with odd degree. What do they mean the sum for the odd degree vertices? We started with that assumptions, right? That there are odd number of vertices with odd degrees. What do they mean by the sum of odd degree vertices? The sum of even degree vertices will be even. Okay, I will have to reread this. I'm getting confused. Which of the following is the definition of a function if a to b being injective? At most, codomain. Every element of B is the image of at most one element. Every element of A is sent to at most one element of B. This is just part of the definition. Oh, at most one unique. So, yeah, it has to be definite as well, right? Every element of B is the image of at most one element of A. This is correct, yeah. When would you likely use element chasing as part of your proof? Element chasing. The proof of 1.5.3 is what is sometimes called an element chasing proof. By definition of subset A, subset B means every element of A is an element of B, or equivalent T for all x. If x is an element of A, then x is an element of B. One way to prove this is to chase the element x from A to B. Let x be an element of A. Since A is a subset of B, we know that x is part of B. Since B is a subset of C, then x is part of C. Therefore, A is okay. Yeah, okay, I understand. When proving that one subset is a subset of another, given sets A and B, the intersection of A and B written A intersection B is the set of all elements that are in both A and B. Suppose you want to write the proof that A intersection B is equal to B. then B is a subset of A. Oh, yeah, yeah, that makes sense. If B intersection A is just B itself, then that means B is a subset of A, which would be a great start. Let A be an element of A intersection B. I think this would be a great, maybe this, not to a direct proof. Let A be an element of it. No, this. The relation is perpendicular to on the set of lines on the plane. This is perpendicular. All right, then I will end the stream here. I want the answers to these questions. Never mind. I will end the stream here. And yeah, I'll see you guys next time then. Bye.